Hello students, I am Dr. Shomakar Chakravarti. So today we will be discussing magnetic materials. That is the last topic in our module 3. Okay. So actually we don't have a detailed magnetic thing in our syllabus. We only have to cover some basic definitions of the magnetism and all some characteristics of some basic magnetic materials. Okay, so let us start. Generally what happens is that by magnet what we mean from our childhood days is that piece of material in which the iron will be attracted, and that is known as magnet. Okay, but that is good for our childhood days, but now the definition of magnetic or magnetic material is different. uh, Probably some of you will be stunned to know that there are material like copper, iron, they are also magnetic material. Platinum, aluminum, chromium, manganese, they are also magnetic material. So magnetic material doesn't mean it has to be attracted by a magnet. So there are some other thing also. So we'll be discussing all that is there. So let us first try to understand what is magnetic field and all. Okay. So there is something called magnetic induction. So we have two things. One is called magnetic induction, which is denoted by B. In some book they call it magnetic field also. In case of magnetic field we put it like this. And there is something called H, which is the magnetic field intensity or magnetic field strength. This is denoted by H, and they are not same. Basically there is a very little difference between them, and it is exactly not clear how you should put it, because different book has written different thing. If you go back to Griffith's electrodynamics book, he has written some interesting thing. He has written that magnetic field is denoted by B, and there is something called H which is not known. So he doesn't prefer to call H anything, he only call magnetic field is B. Okay, so for the time being we will call it magnetic induction. So magnetic induction represents the magnitude of internal field strength within a substance subjected to a field H. So that means if I have a substance here, okay, and I put a field, this field is H, okay, so the magnetic, there will be induced magnetism, like induced dipole moment, there will be induced magnetic moment, so induced magnetism, and this field within this is denoted by B. Okay, so this is called that. Okay, so basically B is my magnetic flux density. Okay, so this is magnetic flux density, and H is magnetic field intensity. So in some respect it is the external one, this is the internal one. Okay, so B, the relation between B and H is B equal to mu into H, or this is mu 0 mu r into H. This is like D and E in electric field, D equal to epsilon E. Okay, where mu is permeability, okay, so the mu, it is Weber, the unit is Weber ampere per meter, so this is known as Henry per meter. The units are not very simple here. Okay, so we have to do it like this only. For H the unit is ampere per meter, and for B it is Weber per meter square. Okay, then there is something we have to know, this is called as magnetization. Just like polarization, I have something called magnetization. So there are a lot of similarities between electricity and magnetism. So once you do the electricity carefully, you can understand the magnetism very easily. So polarization was the dipole moment per unit volume. So this is magnetic moment per unit volume. Okay, so magnetic moment per unit volume. Okay, and this is denoted by M. Then also we have something called magnetic susceptibility, as I have told you in the previous class. So we denote it by chi m, the magnetic susceptibility. Okay, so what we know is this magnetization m is directly proportional to the applied field, just like the electricity case. So this is directly proportional to the H. This is applied field, applied magnetic field, obviously. So M, we can write it as chi m into H. So we can write chi m equal to m by H. Okay. We can find out the relation between this B, H and M, okay, easily. So let us try to do that. Relation between B, H and M. Okay. So from Ampere's law, we know curl B equal to mu naught J. Okay. But this J is actually J free plus J bound. That means there are some free charges and also the bound charges. Now for the free charge we know, for the bound charge, J bound is related to our magnetization. So this is curl of M. So we can write curl B equal to mu naught J free. I am writing JF by J bound. This is equal to mu naught curl of M plus J free. So we can write J free is equal to curl of B by mu 0. I am taking this minus M. Okay. Now we defined H. So actually the H originates like this. H equal to B by mu 0 minus M. So we have B equal to mu 0 H plus M. So this is one of the important derivation that you have to remember. And then from this is like D equal to epsilon 0 E plus P. So D equal to epsilon 0 E plus P in polarization, what we have done in case of dielectric. So similarly we have M equal to chi M into H. So we can put B equal to mu 0 1 plus chi M into H. So we can write it as mu H is equal to mu 0 1 plus chi M into H. So mu 0 mu R equal to mu 0 1 plus chi M. So therefore my mu R is equal to one plus chi M. So this is another important derivation. Now let us discuss the three main magnetic material we are having. Okay, so basically we are having three magnetic material. One is called diamagnetic, then the second one is called paramagnetic, Then one is called ferromagnetic. So basically we are having three magnetic material, mainly these three. There are other 2-3 branches also, which is very obsolete, very small actually. We'll come into that. Okay. So what happens is that there is in diamagnetic no permanent dipole. No permanent dipole. But here in other two cases, the paramagnetic and the ferromagnetic is little bit similar. Only thing is that ferromagnetic is something like 1,000 or lakhs time of paramagnetic. So they have permanent dipole. Both of them had permanent dipole. Then if I place a diamagnetic material in magnetic field, okay, what happens is that it acquire a feeble magnetism in opposite direction of the magnetic field. Okay, so this is it acquire very small magnetism in opposite direction of applied field, and this is very interesting. And due to this, it is repelled by magnetic field. That means if you put a dielectric material, it will be moving opposite to the magnetic field. Okay, and in paramagnetic case, it acquire feeble magnetism in the direction of magnetic field. It is not the opposite direction, in the direction of magnetic field. Okay, so it is attracted feebly by the magnetic field. In case of ferromagnetism, what happens is that the dipole tend to, they already have dipoles, so they acquire high magnetic field. Acquire high magnetism and therefore attracted towards magnetic field. And this is the actually the ferromagnetic materials are the material which we call it like iron is attracted towards magnet and all. Okay, now let us try to understand this quantitatively within some value. Okay, why this is happening? Why this is happening? Because here chi m, that is susceptibility, is negative. That means magnetic field is actually expelling out of that material. Okay, I'll draw that, and mu r is less than 1. Okay, here chi m is positive and it is of the order value 10 to the power minus 6 and mu r greater than 1. For ferromagnetic, here also chi m is positive, but look at the value. This is 10 to the power 6 times, this is 10 to the power minus 6, but it is 10 to the power 6. And this mu r is actually very greater than 1. It is nearly 1000, and that is why it is strongly attracted. Okay, so what happens is that in this case, if I have a diamagnetic material and if I have the magnetic field like this, so field lines actually go out of this. So maybe only one goes in. Okay, here actually what happens, if I have a field here and I have this, so maybe one will go and there feebly it is going like this. But if I have this, so this is strong magnetic field will be going towards this, means even this magnetic field may be going towards this. Okay, so that is why they are different. Clear? where you can see this diamagnetic material can be seen for material having outermost orbit even number of electron. So outermost orbit has even number of electron. This is for outermost orbit having odd, so there will be odd number of electron. For ferromagnetic, we don't have this. They are actually done by some domain. They have some domain. Okay, it is written there in my copy. And then the last example is here: copper, silver, Au. Paramagnetic material is platinum, aluminium, chromium, and here it is iron, nickel, cobalt, etc. If I plot it, the if I plot the applied field by magnetization, then I can show you that paramagnet is like this. Ferromagnet is some very large value, 1000 times of this. So this is paramagnet, this is ferromagnet, and diamagnetism is negative. It is opposite to the magnetic field. So this is my diamagnetic. Okay. Now we will be calculating the magnetic moment of an electron, and that is the basic starting point of the magnetism. Why we can see a magnetism? Because an electron, okay, so if a current actually passes in a loop, that current actually produce a magnetic field, and in a magnetic field, that means there is a magnetic moment. So basic charge particle is the electron. So if a electron, let us say I have an electron moving at a radius r, okay, so how to calculate the magnetic moment? This is very, very important, this derivation. So current, I can write I equal to E by tau. Tau is the time of revolution. Okay. So tau is nothing but 2 pi r, that is the circumference, divided by the velocity. Therefore, I can write I equal to EV by 2 pi r. So magnetic moment of a dipole is, remember this, it is given by mu m, that is equal to current into area. Okay, so mu m equal to current into area. So this is EV divided by 2 pi r into pi r square. So this is half EVR. Okay, so now we know orbital angular momentum L equal to mvr, and by Bohr's theory, by Bohr model, we have mvr equal to nh by nh cross. Okay, therefore I can put vr equal to nh cross by m. H cross is h by 2 pi. Okay, remember that. So I can write mu m, that is this, is equal to half into E into VR. VR means this. This is NH cross by m, so this is n e h cross by 2m, so mu m is n into e h cross by 2m, where n is the number of orbital. Okay, so e h cross by 2m is known as Bohr magneton, that is the magnetic moment for an electron revolving in the first orbit. It is denoted by mu b, and you have to remember the value. This is a constant 9.274 into 10 to the power minus 24 ampere meter square. Okay, so this is the calculation part of it. Now let us try to understand the domain theory. Okay, uh, why it is, what do you mean by a domain theory? For ferromagnetic material, it was not clear why the ferromagnetic material behaves like this. Okay, so it was understand that ferromagnetic material actually contains small region. Okay, so it contains small region, and the region is something like this. The dimension of the region is 10 to the power minus 6 to 10 to the power minus 2 centimeter cube. Okay, and there are about 10 to the power 17 to 10 to the power 22 atoms. So you can understand how many domains are there. So what happens is that in normal cases the domains are aligned randomly. When you apply an electric field, the domain tend to align themselves in the direction of the field, and that is why you see a huge magnetic field in the direction of the magnetic field. Okay, so what happens is that it is just a basic idea. Okay, so initially what happens is that they are randomly oriented, and this is the domains and they are the domain wall. So net magnetic moment in this domain is this. So domain are small region, and this region may have domain in this magnetic field in this direction, another domain may have magnetic field in this direction, like this. So magnetic moment can be in different direction. So here the net magnetic moment is 0 in this case, because it is evenly distributed. Now if I apply a magnetic field, so what happens is that let us say I am applying the electric magnetic field in this direction, so this will be try to align itself in the direction and they will try to decrease. So what happens is that the domain will shift. Okay, so it will be like this, so it is increasing. Next one, it will go like this, so this is this, and finally what happens is that this will dominate and all the domain movement will be like this. Okay, there is something called Curie-Weiss law. We will not again go to the derivation of it. Okay, you have to only know the statements that for ferromagnetic material this is given by C divided by T minus theta F. Okay, so chi m is the susceptibility. So susceptibility of a material is given by this, where theta F is called the ferromagnetic Curie temperature. So above this temperature it will be a paramagnetic one. Okay, then let us come to the another topic called hysteresis. Okay, what happens is that if we have a applied magnetic field, and we are measuring the field inside the material, some ferromagnetic material. So this is basically for a ferromagnetic material, this can be seen. So what happens is that initially I'll start from 0, okay, and I will reach some value. Okay, so if I increase the H value, B will increase, and eventually it will reach some value and it will reach a constant, and beyond this if we go on increasing it will be constant. Okay, Now what I do, I keep on decreasing the value of h. So if I decrease the value of h, it doesn't follow the same path as this rise. So it follow a different path and it come here. Okay. So then what happens is that up to this it is there. So at zero field there is some field is already there. Okay. So it retain that field. So this is called retentivity. Now, if I want to make it 0, I have to apply another field in the negative direction. Now, if I put that, it will come here. So, it come to 0. This is called coercivity. So, I have to put a coercive field. Then if I go on increasing it, it start increasing in the negative direction. So, it will come to here. Then again it will come back like this. So basically it will follow a reverse path and it will go here. Okay, the drawing is not a perfect one. Let me draw it another one. So basically it will be something like this. It can be like this, where the area is more, okay, or we can have some material where the area is very less. Okay, so the lesser areas, they are called soft material, they are called, and this is called hard material. Okay, so hard material, what happens is that for hard material, retain certain field even after, even for high change. You see, if it is already here, even for 0, okay, so it is there, so it retain this much of field. Okay, so this is used in magnetic storage. That means if you don't have a field, it will be stored there even if in the absence of this. So this is hard material are used for magnetic storage, whereas there are soft material, they are used for transformers, where if there is no field, okay, so there is no magnetic moment there. Okay, and there is something called hysteresis loss, because there is some energy loss in this process in the case of hysteresis. Okay, and this hysteresis loss can be calculated and it can be shown that it is something related to the area. So let us do that, and that is the last thing what we will be doing. Okay, so magnetic flux phi is nothing but magnetic induction into area, so B into A. Okay, now induced EMF is given by induced EMF is given by N into d phi dt, where N is the total turn in the coil. Okay, so I can write, if phi is this, I can write the d phi equal to A into dB, because A is a constant. So energy loss, that it will be dE, that is current into EMF into time. So current is I into EMF is N d phi dt into time dt. So this is I N d phi. So I N A d B. Now from the definition of magnetic induction, we have H equal to B by mu, or mu Ni by mu. This is for a B equal to mu Ni is a standard thing. This is for any coil. If the number of turn is n is the number of turn per number of turn mu. If current I is flowing, then it is this. Where small n is the number of turn per unit length. Okay, you can go back to your plus 11 book and please have a look at there. So it is Ni, small ni. Small ni is nothing but total turn divided by L. So it is small n is the number of turn per unit length into I. Okay, so what we are having is dE, that is equal to I N A dB. So I into LH by I A into dB, that is equal to A L H dB. So total energy loss E, that is integration of dE, that is equal to A into L into H dB. Therefore, the last thing, energy loss per unit volume is E by AL. Area into length is the volume. So this is HdB. What is this HdB? This is nothing but the area enclosed by HB curve. Okay, and this is called the hysteresis loss. So that means if the area of the curve is more, then the hysteresis loss is more. If the area of the curve is less, then the hysteresis loss is less. Okay. Let us quickly do the last two things. There are two things which is called antiferromagnetic material. So what happens is that in antiferromagnetic material, the dipole moments of the neighboring dipole are equal and opposite in orientation. So what happens is that one dipole is this, another is this, one is this, another is this. So in case of ferromagnetic material, I have all the dipoles in the same direction. This is ferromagnetic. But for antiferromagnetic, I have one is in this direction, another is in opposite direction. So this is called antiferromagnetic material. Example is nickel oxide, iron oxide, manganese oxide. Then something called ferrimagnetic material. For ferrimagnetic material, if the spins of the atom are such that there is a net magnetic moment. So spins are such that there is a, due to the spins there is a net magnetic moment. Okay, so just you have to remember the examples and basic things, because you can expect this question in MCQ. Okay, so that is what we all have in this chapter of magnetism. So we have finished our module 3. Hope you will be able to answer the questions, and if you have any question, you can write in the comment section, or you can get back to me by my email or phone. Thanks.